Welcome back everyone for another SVSU Math and Physics Resource Center video. My name is Brendon, I'm going to be your tutor, and for this video we're going to be getting into part 3 of the ratio test. So yeah, let's go ahead and get into it. Alright, so let's get into the last video of the ratio test. So we're going to get into an example, but let's go back and recap what the ratio test is. So we start with a series from n is equal to k, which is just a constant going to infinity, of a of n, which is just a function of n. What we're going to do for the ratio test is we're going to take the limit as n approaches infinity of the absolute value of a of n plus 1 divided by a of n. And if we get that equal to some constant L, we have 3 criteria. So if L is greater than 1, the series is going to diverge. If L is less than 1, the series is going to converge absolutely. And if L is equal to 1, that tells us it's inconclusive and we have to try another series test. So let's go ahead and do this example. So first thing I'm going to do is I'm going to point out my a of n term. And then let's go ahead and write out the a of n plus 1 term. So this is going to be negative 1 to the n plus 1. All over, looks like it's going to be n plus 1 squared plus 1. Okay, and then we're going to simplify this. So there's nothing we can really do to the negative 1 to the n plus 1. We can pull out that extra 1 that's in the exponent, but we'll do that later. So we're going to leave it as negative 1 to the n plus 1 divided by, and so let's go ahead and FOIL this out. So it looks like we're going to end up with n squared plus 2n plus 1 plus 1. And so then this is going to be negative 1 to the n plus 1 all over n squared plus 2n plus 2. Okay, so that's our a of n plus 1 term. And so let's go ahead and fill out this limit. So we're going to do the limit as n approaches infinity of the absolute value of a of n plus 1. So that's this term that we just simplified. So that's going to be negative 1 to the n plus 1 divided by n squared plus 2n plus 2. And then on the bottom is our a of n term, so that's our initial piece. So that's going to be this negative 1 to the n all over n squared plus 1. Okay, so now let's go ahead and simplify this by keeping the top, switching the sign from division to multiplication, and flipping the denominator. So this is going to be the limit as n approaches infinity of the absolute value of negative 1 to the n plus 1 divided by n squared plus 2n plus 2 multiplied by, now we're going to flip the denominator, so it's going to be n squared plus 1 and negative 1 to the n. Okay, so now we're going to simplify this negative 1 to the n plus 1. So we're going to the limit as n approaches infinity of, let's see, it's going to be, when we pull out that 1, it's going to be a negative 1 to the first power multiplied by negative 1 to the n divided by n squared plus 2n plus 2 multiplied by, and then nothing happens to this term, so n squared plus 1, negative 1 to the n. Okay, so we can cancel out these negative 1 to the n's. And then let's see what we have left. Oh, and then one more piece I'm going to simplify here is we just have negative 1, but we take the absolute value of negative 1, and so we're going to end up having it just be positive 1, so we can just omit that from this next expression, because it's just going to be positive 1 times whatever, whatever's left is going to be whatever's left. So we're just going to end up with the limit of n squared plus 1 divided by n squared plus 2n plus 2. Okay, and so we can do this limit. What we're going to do is we're going to multiply both the top and bottom by 1 over n squared. 1 over n squared. Okay, and let's see what we're left with. So this is going to be the limit as n approaches infinity of, let's see, it looks like we're going to have a 1 plus 1 over n squared divided by 1 plus 2 over n plus 2 over n squared. Okay, and so it looks like as then we can plug in our infinity as this piece is going to go to 0 because our denominator is getting really big. Same with this piece and same with this piece. So it looks like we're going to be left with just 1 over 1, which is just going to be 1. So let's go ahead and see what this looks like for our criteria in our ratio test. So L is greater than 1, series diverges. No, we don't have that. L is less than 1, series converges absolutely. We don't have that. So L is equal to 1. This is the one that we're working with. And that tells us that the ratio test was inconclusive. So that means that we have to try testing this with a different series test. And so now we got to determine what series test are we going to use. Well, if we look at this negative 1 to the n, as n goes from 0 to infinity, that's going to make this go from a even exponent to an odd exponent, to an even exponent to an odd exponent, which is going to change it from negative to positive, negative to positive. So then that tells me that this is an alternating series. So I'm going to go ahead and try to do the alternating series test. And if you're not familiar with the alternating series test, I highly recommend going back and checking out that video, which will go into more in depth on how to use the alternating series test. Okay, but the two things that we need to know for the alternating series test is that, well, actually, let's write out the form. So it's going to be the form from n is equal to k, the summation as n is equal to k to infinity of negative 1 to the n, and then some b of n. So b of n is just a function of n as well. Okay, so then let's write out for our series, what is our b of n? So if we take our negative 1 to the n term out of our series, it looks like we're just going to be left with 1 over n squared plus 1. Okay, and so for the alternating series test to show convergence, all there needs to be is b of n needs to be a decreasing sequence, and the limit of as n goes to infinity of b of n has to approach 0. So let's go ahead and show that. Let's show that it's a decreasing sequence. So the way that we can look at that is just by actually looking at the function. So 1 over n squared plus 1. So if I take that and I put in the next term, so let's actually write out a few of the terms. So 1 over n squared plus 1 is equal to, so let's do when n is equal to 1. So 1 over, looks like this is going to be 1 plus 1 is 2. So then we'll do the next one, which is 1 over 2 squared is 4 plus 1 is 5, plus 1 over, and then this is the last one we'll do, 1 over 3 squared, which is 9, plus 1 is 10, and then plus dot, 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 so and so on. And so the way that we can tell this is decreasing is our numerator isn't changing, but our denominator is getting bigger and bigger, and it's going to continue to get bigger and bigger. So that tells us our sequence is decreasing. Okay, and so now we just need to show that the limit as n approaches infinity of b of n, so 1 over n squared plus 1, we need to show that this is equal to 0. And actually, it is going to be equal to 0. And the reason is because as we plug in our infinity to the denominator, our denominator is going to get really, really, really big, and our numerator is going to stay the same. So that tells us our function is going to be approaching 0. Okay, so through the alternating series test, we were actually able to show that the series converges. Okay, and so that's what you're going to have to do whenever you run into this inconclusiveness with the ratio test. So yep, so we went through the ratio test, we got it equal to 1, tells us it's inconclusive. We noticed that the series was alternating, and then we went ahead and ran the alternating series test to find convergence. All right, guys, hope you enjoyed the video and you learned a little bit. Thank you.